Hi everybody, hope you're all having a good day today so far. Today we're going to be talking about correspondences and hemicontinuity. Now let's start right off by recalling that functions are single valued. A very short to the point statement, but in economics it turns out we very often need to use what we call set-valued functions, functions where the image is not a point or an element, but is rather a set. So let me just start right off by giving a couple of examples from consumer theory where this is something that we need. So let's draw the space of prices. Let's suppose there are only two goods. Keep things simple. We have a wiggly axis here. That shouldn't make any difference for us. We know, of course, that the consumer's budget set is going to depend on the prices. So let's start off with a price list here where the second price is larger than the first price. And so the budget set for our consumer, for let's say some given amount of his budget, that's going to look something like this. And then for a different price list, let's say a price list down here, and I think I want to use a different color for this. Let's use this orange color. Let's call that price list P prime. And here the first price is larger than the second price, so the budget set is going to look something like this. And so in particular then, we have a kind of a function, if you like, going from price lists not to points in R2 plus over here, but to subsets. So we could call this function B for the budget set function, and it goes from price lists in R2++, and I'll just use strictly positive prices to keep things simple here, and it goes and maps into R2+. And so a function in the usual sense would pick out an element of R2+, and that's what this notation with the arrow means for us. That's what we mean by this notation. So here, though, what the function, set-valued function, B picks out is not an element of R2+, but a subset of R2+. So let's take off this element symbol here, if we can get it off, and we will replace it with a subset symbol. And so for every price list over here in R2++, B of P here is a subset of R2+, of a certain kind. And so this isn't a function in the usual sense, so we don't want to use this notation. And the notation we actually use is, for this, is a double arrow-headed arrow. And so this set-valued function describes how the consumer's available or feasible set, budget set, depends on the price list. Second example is, let's say, a demand function. So usually we have a demand function, again defined on strictly positive prices, that for any price list picks out an element of R2+. And so let's suppose that we have a consumer who has a part, let's say, of let's say her indifference curve looks like this. And so this consumer would be picking out this point here as the one that maximizes her utility if the budget set comes from the pink price list, if the pink budget set is the appropriate one. And so indeed we would have D of P, an element of R2+. But let's suppose the consumer's indifference curve actually looks like this. here. So along this line segment here on the budget constraint, right in here, the consumer is indifferent between all the different bundles on that line segment. So the consumer might pick any one of those bundles. So we can't say that there's a specific element of R2 plus that will be chosen by this consumer at the, at the orange price list, P prime, but rather the consumer isn't, of course, going to choose a set. So that's not what we mean here, but rather that there's a set of things that the consumer might choose. And so we identify the set of all the things that the consumer is indifferent amongst and might choose. And again, we need to replace the element symbol with the subset symbol. And so for any price list, this tells us the set of bundles that the consumer might choose. And for this situation here with the pink price list, here the consumer, we can say, does pick a specific bundle, but since we need this to be a subset, it would be a singleton set rather than just that point. So there's just two examples, prominent examples in consumer theory that you will see where we need to use set-valued functions. And of course I should add here that this should have this double-headed arrow here. And so here are four more examples. I'm not going to go into detail about these examples, but four more examples from economics and game theory where we need to use set-valued functions. We have two examples from the theory of the firm. We have substitutability of inputs, and we have constant returns to scale. Both of those are situations where the firm's production technology has one or more flat spots of some kind, one kind or another, much like the flat spot on the indifference curve here. And so because of those flat areas in the firm's production technology, again, we have a not completely determinate behavior by the firm at a given price list, and we need to use similarly some kind of set-valued function to describe the firm's behavior, the firm's decision-making. And then we have two examples here from game theory. The first one, mixed strategies. If we want to take account of mixed strategies when we're working in game theory, we absolutely need to use set-valued functions. And in fact, if we go back to, I think the first place, if I'm not mistaken, where set-valued functions like this were used in economics or game theory was in John Nash's original paper back in 1950, where he introduced the notion of a game theoretic equilibrium that immediately became known as Nash equilibrium. And in that, he was using mixed strategies, and he needed to use what he called, I think, one-to-many. For any one element here, you got many possible elements over here. I think he called it a one-to-many function. It's a set-valued function. And then action availability in game theory. By this I mean that we often have situations where the actions that are available to a player depend on the actions chosen by the other players perhaps. So again, we have a function from the other player's actions to a set of available actions to the player we're investigating. So here we just have six examples of situations in economics and game theory where we need to use set-valued functions. So now let's take what we've done so far and let's actually write down a formal definition of what we mean by a set-valued function, which is what we have here. And in fact, set-valued functions are typically called correspondences. And a correspondence, then, the definition of a correspondence or set-valued function is really just writing down what we've already said in words, the correspondence from one set x to another set y, this would have been playing the role of x here, and this would have been playing the role of y. And so our set valued function, or maybe it would even be a good idea here to write this as a double-headed arrowhead. A set valued function, or correspondence, we write it the way that we've said, with a double-headed arrow. It's a function from the domain, capital X, to the target space, which is not capital Y, but it's the set of all subsets of capital Y. So we could, of course, write it as f from capital X to 2 to the y, but instead we write it, and that would be a function, instead we write it this way to indicate that it's picking out a subset of y. As it says here, for every element of the domain, every x, f of x is a subset of capital Y. And these correspondences are also called set-valued functions or multi-valued functions. As I indicated, John Nash actually referred to it as a one-to-many function. That isn't really used anymore. And the notation with the double-headed arrow, that's not the only notation that's used. We also, I'll write that one here, some people use this notation instead. Some people use this notation. And I believe I've even seen this notation, if I'm not mistaken. And I think this is the one here that most people use now, but I will say that I think the person who first used this, the first time it was used, that was me. In a paper in the International Economic Review a long, long time ago. I believe I was the first person to use this notation, and it seems to have been picked up by just about everybody else as the notation they typically use for correspondences. And so let's now give several simple examples, or let's say examples of kind of simple correspondences. Here's our first example. And in this example, we have a function, a correspondence, f, and for every element of the domain, here the domain is r plus, it's the x's in the diagram, and the target space is all of r, so it's all the positive and negative values of y. And for every x, every element of the domain, f of x is a set. It's either a singleton set, the set consisting of just the origin, or it's a two-point set, set consisting of both the positive and the negative square root of x, and that's what we see in the diagram here, where for any given x, we have both the positive and the negative square root. And for a second example here, we again have a correspondence for which for every element of the domain, for every x, the correspondence picks out either a singleton set, the origin, so right here, or a two-point set consisting of 0 and 1 over x. By the way, I said this was the origin. That's not right. It's the number 0. It's not the origin. That was a mistake. It's picking out the number 0, the singleton set consisting of the number 0 on the y-axis in the target space, which is, in this case, r plus. And so, again, here, this correspondence, again, every element of the domain, every x, the correspondence picks out either a singleton set or a two-point set. So for positive values of x, the function, the correspondence, picks out 0 and 1 over x, the 2 points. Third example, here it's really pretty much like the second example, except that here I've written the example so I've filled in the area between the lower bound and the upper boundary of this of this area here. So here the correspondence picks out either a singleton set, that is, it picks out the set consisting of just 0 when x is 0, or it picks out an interval, a closed interval, the interval from 0 to 1 over x. So for positive values of x, the image of x is everything from 0 up to 1 over x, 0 up to 1 over x, 0 up to 1 over x. So it's an interval. And for our last example right now, we have this correspondence, which maps from the unit interval into the unit interval. So in this picture here, in this diagram, here we have the unit interval that's the domain, and here we have the unit interval that's the target space. And so the graph of this correspondence is in the unit square. It's in the cross product of the unit interval with itself. I haven't marked off the endpoints 0 and 1 here or here. What I've laid out is every 10th here. So here we have 0, we have 0.1, 0.2, 0.3, and so on. So f of x, the image under f of a given point x, in each case is either an interval, a closed interval in the y set, in the target space, or for values of x between 0.4 and 0.6, here it is the union of two disjoint closed intervals. So the graph looks like this, where we have for any x over here to the left of 0.4, the image is an interval here. For anything to the right, it's an interval here, and for values of x between 0.4 and 0.6, it's the union of this interval and this interval. And so that's just 4 simple examples of correspondences, and we're going to see several more examples when we try to develop the idea of hemicontinuity. The next thing we have here is the notion of a selection from a correspondence, and all that is just a function. So I've used g here to name the function, which is a single-valued function, which is a selection from the correspondence f. Let's take this example here. A selection g from this correspondence here would be, again, a single-valued function. So for the element 0 in the domain, since f of x is the singleton consisting of just 0, the selection would have to pick out 0 as the image under g, the function g. But then for all the other x's, our selection g could pick out anything in f of x, because f of x is an interval along the real line, along the y-axis here. So it could pick out any point in the shaded area here. And in fact, a selection doesn't have to be continuous. We often work with continuous selections, but in general, a selection is just a function, not necessarily continuous. So it could be not here because it has to pick out 0 for x equals 0, but for all the positive x's, it could be jumping around, all around. It could be jumping from the top border down to the bottom border, back to the top, anything in the middle. It doesn't have to be continuous at all to be a well-defined selection. So what if the image at a particular x in the domain in the correspondence is, remember, it's a set. F of x is a set. What if it's the empty set? That's allowed in our definition of a correspondence. Well, if f of x is the empty set, then I can't find anything to define as g of x for that x, because g of x is supposed to be an element of f of x, but there aren't any elements in the empty set. So we only define selections for what we call non-empty valued correspondences, correspondences that have a non-empty set as the image for every x in the domain. And in fact, you'll even see And it's not at all uncommon for some people to define a correspondence in such a way that the correspondence only picks out non-empty subsets. So when we see this over here, of course, these aren't the empty set, but in general, defining a correspondence, our definition allows for the empty set to be f of x for some x's. As I say, some people, they define it to be just non-empty sets, so this problem doesn't arise there, but other problems arise elsewhere. There's some trade-offs in the definitions. Now, I just used the term non-empty valued for a correspondence, and here's a formal definition of the notion of a non-empty valued correspondence. It's really just what the words say. That is, a correspondence is non-empty valued if at every point x in the domain, the image f of x is a non-empty set. And in fact, we use the same kind of terminology for a bunch of other properties that sets have that we then can transfer to the images of the correspondences. So, for example, we say a correspondence is closed valued if, for every point in the domain, the image is a closed set. We say that the correspondence is convex valued if, for every point in the domain, the image set is a convex set, and the same for compact valued, singleton valued, and so on. And so, actually, let's go back for just a moment and look at each of the four examples that we just did and see which of them is convex valued, closed valued, and so on. So each of the first two examples, the image of every point in the domain is either a singleton set, 0, or a two-point set. And so since both of those kinds of sets are always closed and in fact compact, both of the first two examples are closed valued and compact valued, but not convex valued, because a two-point set can never be convex. So that's the first example. Second example, same thing. Third example here, the image f of x is either 0, the singleton set 0, or the closed interval from 0 to 1 over x. Again, both of those kinds of sets are always closed and compact. So this is a closed valued and a compact valued correspondence. But this correspondence is also convex valued because, of course, the singleton set any singleton set is going to be convex. And when the image is an interval, again, intervals are always convex. So the image is always a convex set, so this is a convex valued correspondence. And the last example, again, the image here is always either a closed interval or the union of closed intervals. So the image is closed and compact. So this is both a closed valued and a compact valued correspondence, but is not convex valued because the union of the two disjoint closed intervals is not a convex set, so the image isn't always convex, so it's not a convex valued correspondence. So we have one last property of correspondences that we need to look at briefly before we turn to looking in detail at upper and lower hemicontinuous correspondences. And that last property is the notion of a closed correspondence, which is very closely related to both upper and lower hemicontinuity, as we'll see in a few moments. So a correspondence is said to be closed, not the same thing as closed valued. The correspondence is said to be closed simply if its graph is a closed subset of the space x cross y, the set x cross y, where the graph lives, if you like, okay? And so this sequential statement down here at the bottom is exactly that. The graph of f is a closed set in x cross y. And that might be a little more transparent if we point out here that this statement for every n, yn is in f of xn, is actually exactly the same as another statement that may be a little more as I say, a little more transparent here. So we have yn is an element of x, f of xn. That's exactly the same statement as the ordered pair xn yn is an element of the graph of f. And so this looks a lot more like what we would say for a closed set. And so we have of course, the universal quantifier in front of each one of these. So this statement down in the bottom, we could replace this with this, and it might be a little clearer that this is saying the graph of f is a closed set. But this is often is easier to work with and to think about when we're talking about correspondences, which is why we usually state it this way. Again, let me point out that closed correspondence is not the same thing as a closed valued correspondence, and we will see in a few moments one or more examples of closed valued correspondences that aren't closed. So let's take a little break right now. We'll take this off so we have a little more space to work with, and then we'll come back and we will dive into upper and lower hemicontinuous correspondences.